conventional machine learning theories believe a lot of parameters make overfitting, and the overfitting make your algorithm test accuracy worse. So many people try to invent some generalization technique to avoid such overfitting issue with high number of parameters. There are many generalization approaches so that with high number of parameters, we can still keep very nice test error or test accuracy. Deep learning cases, this is more important because usually deep learning has a lot of parameters. Especially after residual network, we can stack hundreds or thousand layers successfully. So we can train millions or billions parameters, and recent GPT-2 or BERT also have a lot of parameters. And a lot of parameters means we have to deal with overfitting issue. Overfitting is kind of a memorization issue. So your function basically do not learn some hidden patterns or some trend in your data point. Instead, your algorithm just remember the input and output pair and just give the output for a given input using the memory. The memorization property is pretty bad property because when you observe new input data point, you have no idea, so your guess for the new observed input is just a random guess, so you cannot expect any nice performance. But if you can learn hidden patterns or hidden trend from the previous data point, you can well expect or well estimate the output of your new observation. Okay, so that's why we have to consider many generalization technique so that your algorithm do not remember, but the algorithm can learn something from your data point. So for machine learning and for deep learning, there are many regularization technique. Famous one I can list: weight decay, dropout. I think batch normalization also a generalization technique. Stochastic gradient descent also a generalization method. Early stopping also a generalization method, I think. Early stopping. So I think we can categorize the regularization technique into three different parts. The weight decay algorithm comes from some additional cost function idea. The dropout in batch normalization comes from some random noise technique. And SGD and early stopping related to optimization technique. Okay. So first, cost function. So basically, machine learning means learning a parameter from your data. And how to learn your parameter from data, we first define a loss function, and the loss function of your parameter, so weight value and bias values of your neural network. and find the best parameter that minimizes the loss function is your target learning process. Machine learning always indicate this process, finding the best parameter that optimize your loss function. Okay, but it is very difficult to find the zeta star, especially for deep learning. The loss function is very complicated. This is not convex function, so simple gradient descent rule cannot give you the best zeta star. And also, because there are too many training data points, we cannot utilize full batch gradient descent, the original gradient descent algorithm, without any noise. But we always have to randomly guess gradient at the current point using mini batch. And this algorithm is called stochastic gradient descent algorithm. And the stochastic gradient descent algorithm updates your parameter theta t plus 1 using theta t plus, minus gamma gt, and here gt is some kind of random gradient vector which obtained from mini batch, and the expectation of gt is equal to gradient of loss at theta t. So this is stochastic gradient descent, and because of this noise, we usually cannot make your loss function is optimal. So there are always some gap between L zeta t, the loss function at current point, and the true optimal loss value. And this gap actually can give you better generalization performance, because zeta star usually has almost zero error, and zero error and very well fitted model, which means you can perfectly explain your input and output pair. And perfectly explain input and output pair means you can definitely remember all the input and output pair correlation. So this is good for your training data point, but this is not good for your test data point. So the SGD, stochastic gradient descent algorithm, is bad because it has some noise and you cannot convert it to your best point. So in a sense of optimization, stochastic gradient descent algorithm is pretty bad. But in terms of generalization, because stochastic gradient descent cannot go to your optimal point, but let's say this is a kind of contour of your loss function surface, then your stochastic gradient descent algorithm just randomly move around your optimization point, and this point usually have better generalization properties. So in terms of test error, zeta t can be better than zeta star, and this is true in practice. And even more, we can stop earlier than usual. So we can stop before your trajectory close to the optimal zeta star, so that your point can be far from the training optimal point, zeta star. Then the gap is bad in terms of your optimization purpose, but this gap can give you better generalization property. So early stopping also is a trick that make your solution can be far from the true solution. So this is bad for your optimization, but this is good for your generalization gap. Okay. So in that sense, so on this line, batch normalization dropout or drop connect. It's very nice generalization process because they introduce some noise. So which means instead of optimizing L zeta function at each time, we add some noise to this loss function. So instead of optimizing L zeta, we optimize some L tilde zeta. Okay. So because we are looking at some kind of perturbed function instead of true L function, your gradient update cannot converge to zeta star, definitely. No doubt. So this is not good for optimization, but this is good for generalization. Noise, additional noise for your training process. This is not good news for your optimization, but this is good news for generalization. So the dropout technique randomly removes some neurons at each time. Drop connect randomly removes some of edges at each time, so that your training network have some perturbations, some random additional noise. So you train not L zeta true function, loss function, but train L tilde zeta, some perturbed function. So this is for your training process. When you train your model, you do not train original network, but perturb your network randomly so that you can learn more general features from training process, which can prevent memorization process and which can more which can make more generalization property. Okay, so which encourage to learn more general features rather than more specific features. But one very important remark for this knowledge-based generalization technique is we have to separate training process and inference process. Inference means the test process. So for training process, it is good to induce some additional noise. It is good to add some additional noise so that your parameter cannot memorize input and output pair. But for inference, because this is not updating your parameter, but this is estimate your output for your given input, there is no need to a perturbation. We don't need to perturb your model because we are not learning, because we want to more accurate prediction. So for example, for dropout case, we do not erase any neuron, but use full architecture for structure of your neural network, and just multiply the erasing probability p. Okay, just multiply erasing probability p for each neuron value, because for training process we only keep p portion of your neural value. So you randomly keep the value with probability p. So when you generate kind of infinite number of randomly perturbed neural network, that on average only p portion of your neuron value will be survived. So when you take average, then the neuron value just becomes the p, the keeping probability multiplied with actual neuron values. So for inference, you just scale your neuron values or weight according to your erasing policy, so that the network can share the same philosophy and same skills as in the training process. But we do not perturb the inference network, since the random noise for inference process has no benefit. It just interfere your decision process, which is not good. We don't want. Okay. Right.